In this video, we'll talk about net positive suction head for pumps. It's related to whether or not the pump is going to cavitate, and we'll talk about what that means in just a moment. If you go ahead and take a look at your screen, you'll see a pump impeller that has been subject to cavitation. And so you can see the impeller down here, but you'll notice that it looks like the edges on the impeller have been eroded away. Actually, they've been eroded away quite significantly in this image. And then this image on the top is of another pump impeller where, again, you can see a tremendous amount of cavitation damage that's occurred. Keep in mind that these impellers are made from solid metal, so they're very strong, rigid pieces of material. So this is quite a bit of damage that's been done to them. And this is cavitation damage. So what cavitation is when liquid turns into a vapor. Instead of by increasing the temperature, which would be boiling, we turn the liquid into a vapor by decreasing the pressure, which is what we call cavitation. So it's effectively like boiling liquid, but doing so by lowering the pressure rather than increasing the temperature. And so what ends up happening is you get your liquid going over the impeller blades. So showing the picture down here, the liquid would come in to this impeller down here at the bottom and then get flung out to the sides. But since these impeller blades, they have a suction side. Let me see if I have a picture here. Yeah, here we are. You can see this is kind of a part of an impeller. So the impeller is rotating around this way, you can see. So the center of the impeller is somewhere down in here. And then you can see the blade of the impeller. And as the fluid comes in, this is the leading edge of that impeller. So the fluid's kind of coming in at this dot here, and then it works its way outward. And so this is the leading edge. And because of the curvature, this section of the impeller blade will be a low pressure region, or we call that the suction side of the impeller. But that'll have a low pressure. And if the pressure is low enough, then you can get cavitation occurring in this region. So what will end up happening is the liquid will turn into a vapor here, and that vapor will move further downstream. So that little vapor pocket will move further downstream and move into a region of higher pressure, at which point that vapor pocket will collapse. And that collapse can occur very violently, and so violently that you can get a shock wave that actually forms from it. So if you had let's say imagine a vapor bubble here, and it starts to collapse inward because it's turning from vapor back into a liquid, it can collapse so violently that you can get a shock wave that forms and propagates outward and impacts on the surface of the blade. And that can cause some structural damage to it, break off a little piece of material. And actually, what actually commonly occurs is that bubble collapses in an asymmetric way. So you actually get bubble that forms with a jet. I'm kind of drawing this sort of poorly here, but the bubble's forming, and then you'll get an asymmetric collapse. So this is the vapor in here. You'll get an asymmetric collapse, and then the jet of water it'll collapse and produce a very strong jet of water in a localized region, and then that will impact on the blade surface and cause some erosion. So when the vapor pockets form, that's not so much of a problem, but when they move downstream and they collapse, that's where you get a lot of damage occurring. And so you can see that a lot of the erosion is actually occurring kind of on the very downstream side of the impeller blades where the vapor pockets collapse. And like I said, the shock wave, the water jet can erode some of the material, and over time you can see the kind of damage that occurs. So it's a big problem. And not only does it erode and damage the impeller, but it can decrease the performance of the pump just because that vapor pocket it sort of blocks the flow of liquid. It doesn't block the flow of liquid, but it decreases the flow rate through between the blades. Let me see if I can show a good picture of it. So we have flow between these blades, and you can imagine if you have a big vapor pocket here, then you don't get as much mass flow rate going through there. So that is a problem. And then the other thing is it causes a lot of vibration in the impeller, which can fatigue bearings and things like that. So that's a problem, and it can create noise, which is also a problem. There may be applications where you just don't want to generate a lot of noise, like on a submarine or something, for example. So you don't want to have cavitation occurring. So lots of reasons why you don't want to have your pump cavitate, so we try to find ways to avoid that. And it's related to the pressure that's generated on the suction side of the pump. So we want to make sure that that pressure doesn't drop below the vapor pressure of the liquid. So there is a quantity that we use to quantify whether or not a pump is going to cavitate, and that's called the net positive suction head. So let me go ahead and find some space here to write that down. So I'll write it here. So NPSH stands for net positive suction head. Kind of a long name, but everyone just calls it NPSH. And there are actually two kinds of NPSH that we're going to talk about in a moment. There's an NPSH required and NPSH available. The NPSH required, or NPSHR, is a property of the pump. It's the amount of net positive suction head the pump needs in order to avoid cavitation. The NPSHA, or the NPSH available, is a pipe system property. It's how much net positive suction head the system can provide to the pump. And what we want is the NPSHA to always be bigger than the NPSHR to avoid cavitation. So I'm going to repeat myself here like I normally do, and I'll write it down. But let me first define what net positive suction head is. So NPSH is defined as the pressure head and the velocity head at the suction side of the impeller, and I'll come back to that in a moment, minus vapor pressure head. So that's the definition of the net positive suction head. So the idea is this: when we have our pump, we'll put just imagine a coordinate system with the origin located at the pump impeller, like right in the middle, so that we don't have any elevation head to worry about. This quantity here is then the total head that's available at the suction side of the pump. The suction side is the inlet of the pump. That's where the pressure is going to be typically the lowest. So like on the picture below here, if we have this pipe system, the suction side of the pump would be right there. It's right where the inlet is. Okay, so that's assuming the flow is going this way. Okay, so that's where we're evaluating the pressure and velocity heads, right at the suction side. Another thing I should mention is we just assume that the flow into this pump is turbulent, so you don't have to worry about the kinetic energy correction factor there. It's just assumed to be equal to 1. So here's the suction side of the pump head, and then this is the vapor pressure head there. The PV is vapor pressure for whatever liquid you're dealing with. And keep in mind that when you look up the value for vapor pressure for like water or something, it's typically given in terms of absolute pressure. So with that in mind, you just need to make sure when you evaluate the total head at the suction side of the pump, that pressure is also in terms of absolute pressure. You just want to make sure that this pressure and the vapor pressure are either both absolute or both gauge pressures. Okay. Typically, it's their absolute pressures. Okay, so I had mentioned that we have two different kinds of NPSH. There's NPSHR, that's the required, or let me write this a little differently. Let's say this is the NPSH required by the pump to avoid cavitation. That's a pump property. So when we talked before about how we had these head performance curves for pumps and they're supplied by the manufacturer, the NPSHR curve is also provided by the manufacturer. And typically it's just found experimentally. And I'll say in a moment how you would find that experimentally. So it's just a property of the pump provided by the manufacturer, typically found experimentally. Then we have the NPSHA, that's the NPSH available from the pipe system. This is a pipe system property. Okay, it's independent of the pump. This is the NPSH that the pipe system provides to the pump. And we find that via the extended Bernoulli equation. And I'll do a quick little example to show you what I mean here. So this is a pipe system property. It's the NPSH that the pipe system provides to the pump. And in order to avoid cavitation, we want, let me write this down, to avoid cavitation, what we want is the NPSHA to exceed the NPSHR. Okay, we want to make sure that what's the NPSH that's made available by the pipe system is more than what's required by the pump. Okay, so the NPSHA is something we calculate based on the pipe system. It'll vary, you know, if you have a pump, it'll have an NPSHR, that's a property of that pump, but the NPSHA, which is a pipe system property, it can vary depending on the kind of pipe system you have leading into the pump, right? It all depends on the pipe system, what kind of valves you have, what kind of lengths of pipe you have, the elevation changes, etc. Those will all affect the NPSHA. And we just want to make sure, to avoid cavitation, that NPSHA is greater than NPSHR. That's a really important thing there. Now, normally there's a little bit of a safety factor there. Like the typical recommendation is to make sure that NPSHA is not only bigger than NPSHR, but you want to put in like a 10% cushion there as well. And if it's a critical application, you might even want more than that. Okay, so you don't want it to be right on the edge of cavitating. You really want NPSHA to be much bigger than NPSHR, if at all possible, just to try to keep you far from the possibility of cavitating. So let me go ahead and show you how we would calculate the NPSHA for a particular pump system. So let's say we have this system shown up here. Just we're pulling water from some reservoir through a pipe system and through a pump and on out. And then the pump is located a height h above the reservoir. So to calculate the NPSHA, what we'll do is we'll just make use of this definition for NPSH. And we'll just use the extended Bernoulli equation. So we'll do the extended Bernoulli equation from point 1 here on the free surface. We'll follow some stream tube that ends up at point 2 here. Point 2 here is right at the suction side of the pump. Okay, it's just leading into the pump. Remember that NPSH is defined based on the conditions that the total head right at the suction side of the pump. Okay, so that's why I'm ending point 2 right there. So we'll do the extended Bernoulli equation. Okay, so here's our extended Bernoulli equation between points 1 and point 2. So here is the total head at point 2, the suction side. Point 1 is right here at the free surface. This is the head loss between points 1 and 2. I put the 1-2 here just to re-emphasize that this is the head loss between points 1 and 2. So, for example, here we don't care about any of the losses downstream of the pump because that's not between points 1 and 2. It's only the head losses between those 2 points. And then this is the shaft head between points 1 and 2. Note that the pump is downstream, so we don't factor that into our shaft head term, because there is no pump between 1 and 2. The pump occurs downstream of point 2. Okay, so when we evaluate the extended Bernoulli equation, so pressure at 1 will be atmospheric pressure. Pressure at 2, of course, is the suction side pressure. I don't know what it is, I just know it's the suction side pressure. The velocity at 1 is about 0. It's a big reservoir, big tank, so the velocity is very small. Velocity at 2 is just, again, the suction side velocity. I don't know its value. It doesn't really matter, as you'll see in a moment. Z2 minus Z1 will be the height h, so that's just the elevation difference between those 2 points. So Z2 minus Z1 is h. HL1, 2, I'm just going to leave it as is. For this example, I'll just call it the head loss between those points. And then the shaft head between 1 and 2 is 0 because there is no pump between points 1 and 2. No pump or no turbine. Okay, so then what I'm going to do is I'm going to rearrange this equation to make it look like the form for the NPSH definition. Okay, so I'll have P all over rho g plus, oh, and the other thing I guess I should mention is I'm assuming that the kinetic energy correction factor is equal to 1, that it's turbulent in this system, okay? So I'm rearranging the extended Bernoulli equation to make it look like this. Let me go ahead and just do the algebra here. Let's just make sure I've got everything. I think I have it all here. So all I've done is I've just rearranged the extended Bernoulli equation. Let me kind of circle it here. And I've just rewritten it down here. And I've written it to try to get it closer to the form of the NPSH definition right up here at the top of the screen. So you can see I've tried to keep the left-hand side to look like that term. I still have a little bit of more modification to get it to look exactly the same. Okay, and then here the P atmosphere was just the P1, and the head loss term is just right there. So let me do the final step. What I'm going to do is I'm going to subtract the vapor pressure from both sides, and then I'll also write Z1 minus Z2 in terms of the H given here. So we'll have P over rho g plus V bar squared over 2g on the suction side minus vapor pressure head. And then on the other side I'll have P atmosphere. I need to subtract out the vapor pressure on that side, just to keep my algebra correct. And then I'm going to rewrite the Z1 minus Z2. That's just equal to minus H. So there we go. And so now you'll see that the left-hand side just looks like the net positive suction head. Right? If you look at this, that's the net positive suction head. And since I'm doing this for the pipe system, this is specifically the NPSHA, right? Because this is the pipe system property. I'm doing this for the pipe system, so this is the NPSHA. So you can see the net positive suction head available is equal to the atmospheric pressure minus vapor pressure, turned into a pressure head quantity. Then we have the head losses, and then we have the elevation head. Okay, so this is how we calculate the net positive suction head available. It's just using the extended Bernoulli equation. Now again, we typically want this NPSHA to be as large as possible so that we can ensure that we're always greater than the net positive suction head required. So to find this NPSHR for that particular pump, I would have to go back to the manufacturer's information for that pump and see what the NPSHR is for that. Right? So I'll come back to that in a moment. So now looking at the NPSHA, just a few things kind of stand out about this. Number one, you need to make sure you're using the same types of pressures here for the atmospheric pressure and vapor pressure. Don't use one of these as gauge and the other one as absolute. Just keep them both absolute or both gauge. Typically vapor pressure is given as an absolute pressure, so you'd want to make sure that both are absolute pressures there. Typically you don't have a lot of control over what the atmospheric pressure is. You might have a pressurized vessel, like if I enclosed this vessel here in some dome and pressurized it or whatever, then I could change what the pressure at point 1 is, but often you can't do that sort of thing. The vapor pressure you don't have much control over. It is a function of temperature, so you could change the temperature of the fluid, and that might affect the vapor pressure, but you don't have a lot of control over those things. So that you don't have a lot of control over. Now the head losses, you do have control over. So ideally, again, you want to keep NPSHA large, so you don't want a lot of head losses because you see they subtract away. So you wouldn't want a long length of pipe. You wouldn't want to put too many minor losses in there because you want to keep this NPSHA large. So avoid head losses. And if you can avoid head losses, you keep the NPSHA large. The other thing is you don't want a big elevation difference, right? So here you see it subtracting away. So you'd want to reduce this elevation difference between the free surface and the pump. So you don't want the pump really high, otherwise you're more likely to cavitate. So these are two things you do have a lot of control over, is reducing the losses and reducing height that the pump is above the reservoir. Ideally, you'd want the pump below the reservoir because then you would be adding to the NPSHA, right? It would actually add NPSHA in that case. Another thing that you can see here is, remember that the head loss term looks like the loss coefficients times the velocity head where that loss is occurring, right? So if you increase the flow rate, then the velocity will increase, right? And then you will get less NPSHA. So increasing the flow rate through your pipe system will end up reducing your NPSHA, okay, because of this head loss term. All right. So let me show you what a tip. Hopefully all that makes sense. Now you know how to calculate NPSHA. It's very important to keep in mind that to avoid cavitation, you want the net positive suction head available to be larger than what's required by the pump. And what's required by the pump is a pump property. So let me just show you a little bit about that. Yeah, so here we are. Here's a plot. This came from the internet of a particular style of centrifugal pump. It's kind of, you've seen these plots before. So you have your head rise versus volumetric flow rate down here. And you can see the head curves for this particular pump for different impeller diameters. And then you see the efficiency curves, here are the dashed lines. And then these kind of lighter colored lines are the brake horsepower curves for the different impellers and different speeds. And all these things are functions of the volumetric flow rate. But what I really want to focus on here is this curve down at the bottom. You've seen this in some other video lectures as well. This is the NPSHR curve for this pump. So this is what the pump requires in order to avoid cavitation. And the values for this are given on the vertical axis on the right-hand side. So you can see it's in meters here. So at a flow rate of, let's say, 10 cubic meters per hour, you'd want to make sure the net positive suction head available was at least bigger than a value of about 4 here. Right? So you need to just make sure that the NPSHA has a value bigger than 4 meters in order to avoid cavitation. And ideally, you'd want it even more than that so that you can make sure you're far from cavitation. Okay, so that's how it works. NPSHA is a property of the pipe system. You find it through the extended Bernoulli equation leading up to the suction side of the pump or the inlet side of the pump. NPSHR is a pump property which you get from a plot like what you see on your screen. So let me ask you a couple of basic questions. So let me ask you this. What if, let me go back up to the picture here. For this pipe system shown right here, what if I wanted to add a valve? Okay, I want to add a valve so I can control the flow rate. Where should I add that valve? Should I put it upstream of the pump or downstream of the pump? Where's the best location in terms of avoiding cavitation? It would be downstream of the pump. Because if you put it upstream of the pump, valves typically have a large loss coefficient, right? So if you put it upstream of the pump, then you're much more likely to cavitate the pump because you're going to have a large head loss which subtracts from your NPSHA. Okay, so you don't want to have it upstream of the pump. Now, let's say I have the option to put the pump either up here or maybe put the pump further down here or below the elevation of the tank, which would be preferable in terms of cavitation. It'd be preferable to put the pump down lower. Like I said, if we can drop the pump below the surface, free surface of the tank, then what will happen is this H term will actually, instead of subtracting, it'll add to the NPSHA. So generally, if you have a pump and you're trying to pump water out of a pit or something like that, you try to put the pump as low as possible, and it'll be more effective that way. You won't have to worry about cavitating it. If it's up too high, then if you're trying to pump water out of some pit and you have your pump more than 33 feet above the free surface of the water, then you won't even be able to pump it because you're relying solely on atmospheric pressure to push the water through the system. You're far better off keeping the pump down below in the pit or down as far as you can get it so that you don't have to worry about cavitating the pump, and then you can supply a lot of pressure to pump the water over a long distance. Okay, let's see if there's anything else I'm missing here I want to say. I think I've covered just about everything. Oh, I guess one other thing. I mentioned that you see, let me show the picture again. You can see here that if you increase the volumetric flow rate, you need a larger net positive suction head required. That's because the, we just know from Bernoulli's equation, as you increase the flow rate, the pressure typically drops, right? If you rotate the impeller speed faster and faster, the pump is more likely to cavitate as well, and that's because you drop the pressure over that suction side of the impeller. The faster the impeller rotates, the lower that pressure gets, and it's more likely to cavitate there. So if you operate at a higher speed, like a rotational speed, then you're more likely to cavitate the pump also. All right, I think that just about covers it. We'll go ahead and end it there.